All right. Okay. All right, so I want to finish chapter 12, okay? So let me do that now. And what I have on the screen now, as you can see, and again, I emailed everyone the notes, so you should have it in front of you. You know, that is, you should have it in your, what do you call it, your inbox, email inbox. So just remember that we are dealing with z-scores, also known as standard scores. This is actually how you calculate them. I mean, there might be, I guess, less of a need for them because we have things like Desmos, but it's still good to be able to work with z-scores. You know, it's still good. You should know how to work with them. And remember, the idea with the z-score is you're taking any normal distribution, okay, and you're subtracting the mean and standard deviation. Those values become z-scores. And what's nice about that is z-scores are a little easier to work with. If you remember, I think I showed you this last time. Let me show it again. Let me just, I gotta share this. Let me close that. I did actually show you a table of values last time, a table of z-scores and the corresponding area under the graph. Let me just show that again. I know I have to stop sharing this, so I have to bounce back and forth a bit. Let me see. No, not there. Here it is. Here it is. You can see on this page in the textbook, which again is online, of course, you know, we have these z-scores, and this gives you the area under the graph of the standard normal distribution curve, and it's to the left of the z-score. To the left. So everything under the, so the area under the graph to the left of the z-score, -3, would be point, what is that, 0.0013. To the left of -2.9 would be 0.0019, and so on. And we can actually use those when we want to get the percentage of data values to the left of a certain score or to the right of a certain score in a standard normal distribution or a normal distribution, but we convert to the standard one. We'll do an example of that today. Okay. We'll do an example of that today as well. Okay. All right. And I mean, with Desmos, what's nice is you can calculate the area more easily because Desmos, you know, is more powerful than, I guess, what we can do in our heads and a regular calculator, I guess. So let me get back to the notes, though. So let me stop sharing this. Okay. Let me also just close this. There we go. All right. Okay, so that's this here. And again, this is, you know, what I was just trying to say before. When you have a z-score from that table, what you actually have is the area under the graph to the left of that z-score. So the z-score would be over here. I'm not sure what this number is, but for now it really doesn't matter. So it's the total, it's the area to the left. Now, it turns out, although it's not easy to prove, that the total area under the entire graph is 1. It's not easy to prove it. Well, for one, this is not a shape like a rectangle or a square, which we have formulas for. And also because the graph extends indefinitely, you know, to infinity, that is, to the left and right, so to minus and plus infinity. But the total area turns out to be 1. What that gives us, and they mentioned it in the table, is if you want the area to the right of a z-score, basically what you do is you get 1, which is the total area, and subtract off this area. And what you'll be left with is this piece. And that's really what I'm trying to show with these graphs. Okay. I mean, they do mention that in the table as well, which is nice. Okay. And with Desmos, again, it's not that, it's pretty easy to do as well. So, and what if you now, I think this is where we got up to last time, but what if you want the area between two z-scores? So let's say you want the area between the z-scores, z1 and z2. So these are just two different z-scores. These are two different data values for the standard normal distribution, or you know, you could think of them as just two standard scores. So basically here, what we do to get the area between the two is we do have to subtract certain values from that table The graphs are illustrating what you have to do. First, you get the area to the left of Z2. We're assuming Z2 is bigger than Z1. So we get the area to the left of Z2 first, either through Desmos or the table, either one. But you get the area to the left of it, okay, by looking up Z2 in that table. Now, then you do the same thing for Z1. That is, you find the area to the left of Z1 under the curve, the standard normal distribution curve. In other words, you look for Z1 in that table, or you can use Desmos. And then you subtract. In other words, you subtract the table entry from Z2 from Z1. You're subtracting area. So you're taking this area, you're subtracting this piece off, and what you're going to be left with is this. That's really what I'm trying to say. I mean, with Desmos, it's a little bit easier because you don't really have to subtract. Desmos can calculate it for you, but it's still good to know how to do this process. I mean, it does take a little visualization, what I'm trying to say. Well, if actually, maybe I can draw it. I guess it's all right. I mean, essentially, again, you're taking the table entry for Z2, the standard score. You're subtracting off the table entry for the standard score Z1 for Z1. You're taking the data, you're taking the table entry, the area for Z2, and you're subtracting off the area for Z1. So we get this. And when you subtract, visually, you're getting this area, and you get the answer. Okay, that's probably confusing, so I think it's good if we do an example. There was an example here I was going to let you try on your own. I'm wondering, though, I think it might be better if we do it together, but let's do this one, though. So we're assuming here that the annual rainfall in a certain region, it's approximately normally distributed, okay, with a mean of 33.5 inches and a standard deviation of 5.6 inches. So the amount of rainfall, the annual rainfall that is, okay, if they like the weather, meteorologists, they like to measure how much rainfall there is. They can get it in like inches and stuff. They're saying that amount annually is 33.5 inches a mean and a standard deviation of 5.6. In other words, we basically have a normal distribution here whose mean is 33.5 and standard deviation is 5.6. So now what we want to know is the percentage of years where the annual rainfall is less than 30 inches. All they're trying to ask you to do is find the area under the graph of the normal distribution to the left of 30. Percentage of data values to the left, that's area under the graph to the left. Percentage of data values is the same as area. Okay? Percentage of data values is the same as area. And in this case, the data values are years. Okay? That's what we're saying here. So for 30, we're going to use the z-score. So we have to find the z-score corresponding to 30. Well, that's what this formula is. We have 30 minus 33.5. Okay, that's the mean. And then the standard deviation is 5.6. So we're dividing by 5.6. So we have 30 minus 33.5 divided by 5.6. And when you do this quotient, you actually get negative 0.625. So in other words, the z-score for 30 inches is negative 0.625. So again, we're looking for the percentage of years, and they're saying that the years here of annual rainfall is normally distributed approximately with a mean of 33.5 inches and standard deviation 5.6. And we're basically trying to get the percentage of data values to the left or less than 30, which is the same as finding area to the left of 30. So we converted to the standard score. But now what I have to do is get that table. So let me get the table here. So I got to share it, and let me stop sharing this for a bit. Okay. Here we go. Okay. Oh wait, no, darn it. Sorry. Let me get to this. Here we go. This is what I meant to do. Okay, there we go. There we go. Okay. All right. So we're looking for negative 0.625. But if you look at the table, you might have to zoom in a bit. Okay. You know, the zoom controls on the left. Negative 0.625 is not here, right? We have negative 0.7, negative 0.6, negative 0.5. That's okay, though. We just round. Rounding, we get negative 0.6. We're rounding to one decimal place. And so what we get is 0.2743. That's the area under the graph to the left of the z-score, negative 0.6. Okay? So now, okay, I know that was kind of quick, so let me now get to the notes again. Then I'll do this through Desmos. Basically, again, you get 0.2743. That's what I'm trying to say. And so that tells you about 27.43% of the years, of all the years they're measuring this, have an annual rainfall less than 30 inches. Less than 30 inches, okay? So again, we're looking for the percentage of data values here, which are years with annual rainfall. In that case, we're going to get 27.43%. I mean, if we did this through Desmos, let me show you how to do this through Desmos. So I got to share Desmos now. Let me stop. Well, you have the notes in front of you, so I guess that's okay if I stop sharing this. Okay. It's coming in, don't worry. There it goes, good. So again, the way we get the normal distribution, right? We can type it in. We can type normal, D-I-S-T. I did show you that last time. Then we do two parentheses. You know, I have showed you that in a previous lecture. I mean, you could leave it blank, because if you leave it blank, it thinks you're dealing with the standard normal distribution, which is 0, which has mean 0 and standard deviation 1. But I'm going to type it in anyway. Doesn't really matter that much, actually. Now, since we're looking for area, we want to check this box. Find the cumulative probability, CDF. And again, what we do is we want the area to the left of negative 0.625. So I type that in, negative 0.625. And you can see we get around like 0.26%. We had to round for the table, right? I mean, if we use negative 0.6, which is what the table had, we get the answer we had on the slides. But if we use the exact answer, negative 0.625, as you can see, we'll get this. But the two answers are close to each other. Remember, we had the round. That's why the value on the slide was a little bit different. But this is what we get through Desmos. This one's a little more exact. And you can see that we're looking at all the data values, the percentage of them, which is area under the graph. That's what we're looking for. All right. All right. Let me go back to the notes now. You know, I will post a video when I get a chance. Let me stop